Good afternoon. My name is Junmo Yang, and I am a Ph.D. candidate from the Department of Robotics and Mechatronics Engineering at DOST. Today, the topic of my presentation is ring pull types of the wearable robotic glove for hand strength assistance. For the past 15 years, wearable actuation platforms that improve hand function have been intensively studied by applying various mechanisms. In general, wearable robotic gloves can be classified according to the driving method, such as tendon-driven actuation, hydraulic actuation, or pneumatic actuation. Although wearable robotic glove is being actively studied, wearability and portability improvements are still needed to effectively assist the user's muscle strength and be practical in daily life. In this study, to overcome the limitations like heavy weight, low adaptability, high cost of production of the existing wearable robotic gloves, we propose a new lightweight, soft robotic gloves using ring pull mechanism, soft material, tendon-driven actuation that can support the muscle strength of the part of the finger rather than the entire hand. A usability test using rubber bands for a total of 10 combinations was performed 7 times for each combination, targeting 20 people. The users completed one experimental participation by repeating grasping and releasing 5 times using the above settings. After repeating the experiment 7 times in this way, a survey was conducted using a 5-point scale to classify the user's comfort level. As you can see in the figure on the right, the combinations 8, 10, and 5 had the highest scores with 4.7 and 4.6 and 4.5 respectively. As shown in the figure on the left, we made a schematic to experimentally determine whether the proposed ring pull mechanism can effectively support muscle strength when applied to each finger. And the picture on the right shows the experimental setup. To briefly explain this experiment, first measure the load set value without wearing a ring. Then, after wearing the ring according to each finger combination, the force when pulled using a motor is measured. Considering the various angles that occur, as a result, the value obtained by adding the force when the ring is not worn and the force of the motor should be measured. However, here we have identified an additional force of 14.82 Newton. This occurred based on the hypothesis that the muscle efficiency was increased and the function of the muscle that had not been used before was activated. In this experiment, a surface electromyography device was used to measure the EMG signal of the relevant muscle in a stationary state where the subject was generating the maximum force. The electrodes of the EMG module composed of 2 channels were attached to the FTS of the forearm. And the figure on the left shows the derivation of percent maximum voluntary isometric contraction value through 2-channel EMG signal processing. Through the results of this experiment, in case 2 using the middle and ring fingers, the largest force was measured and 15.53% lower EMG value was obtained compared to the other 2 cases. Another part of RPSG is tendon driver box part. In the center of the main body, a tunnel that becomes the tendon path is inserted with a rubber tube and is connected to the tendon driver box. For the tendons connected to the 2 rings, coated wire with a diameter of 0.4 mm was used and inserted into the tendon drive box through the tube. And the total weight of the glove part made of soft material was 68.4 grams. The tendon drive box consists of a total of 4 pulleys and 1 DC motor equipped with a worm gear to simultaneously pull and release the 2 tendons. 2 pulleys were used for 1 tendon, and the direction of the pulleys was placed perpendicular to each other. The ring of the RPSG can be pulled and released using 2 switches built into the bottom of the tendon box, and the total weight of the tendon drive box, including all components, is 124 grams. We conducted a test to confirm the performance of the RPSG. The performance of the RPSG was evaluated by measuring and comparing the maximum grip strength of the 7 subjects with and without the RPSG. The experiment was conducted in 2 stages, when the RPSG is not worn and when the RPSG is worn. In the first stage, the subject does not wear the RPSG and performs grasping for 3 seconds using the maximum force that can be generated in a given posture. Repeat this process 3 times at 3-minute intervals. After that, the experiment was performed under the same conditions by changing the grasping time to 5 seconds and 7 seconds. In the second stage, the experiment was performed under the same conditions except for the difference that the subject wore the RPSG in the first stage and then operated during grasping. The video on the right shows when the RPSG is activated with and without the user's intention. The video on the left shows the example of the experiment grasping 5 seconds and 7 seconds with EMG signal. The figure on the right shows a graph comparing the grasping force and the percent MVIC value for each subject. As a result, IROS proved that the subject's grasping force with the RPSG increased of 25.69% on average compared to without RPSG, and percent MVIC decreased by 23.51%. This is conclusion. In this study, we proposed the ring pull mechanism and confirmed the finger combination that most effectively supports grasping force of hand throw experiments. And we developed the RPSG using the finger combination selected through the experiment. Through the performance test, we confirmed that the grasping force increased by 25.69% when the RPSG was worn compared to when it was not worn, and the EMG signal decreased by 23.51%. In the future, we will develop a follow-up model so that it can be actively operated by sensing the contact force of the palm side of the RPSG. Then the feedback control for active flexion and relaxation will be applied by sensing the contact with the target object or the user's force. This is the end of my presentation. Thank you for your attention.